G'day mathletes, welcome back to the channel. It is the school holidays and the sun is shining, so I thought what better time to talk to myself about mechanics for half an hour. So today I'm going to take you through a variety of mechanics questions from recent HSC exams to try and give you a bit of an overview of the whole topic and hopefully help you prepare for what is probably the hardest topic in the hardest course in the HSC. Alright, so let's dive straight in with a question from 2023. This was a band 4 level. Now I know that in extension 1 and 2 there isn't band 2, 3, 4, 5, 6. There's E1, E2, E3, E4. What I say when I'm saying that this question is band 4, I mean that in 2023, students who got this question correct were typically scoring 70% and above. If it's a band 5, they were typically scoring 80% and above. So it doesn't exactly match up with the HSC, but I'm just giving you an idea, okay? Okay, so we have an object of mass m sliding down a smooth plane, a ramp actually, velocity v, t time, angle of the elevation of the slope is theta. We have a object here at this point here. It's got a reaction force from the surface of the plane, which is r. Acceleration due to gravity is g, and no other forces acting on the object. So it's just the object sliding down the plane. I and j are unit vectors parallel and perpendicular, shown here. So j is going this way and I is going that way. So up is positive and up the slope is positive for those two. So there's the setup and there's our picture. For 2 marks, we are going to show that the resultant force on the object as it moves down the plane is negative mg sine theta times I. So the only forces are acting in this direction. There's nothing happening up or down because it's just going down the plane. All right, so we're going to need to make some space and draw a bit of a picture. This question involves us knowing how to break down a vector into its components, which is a hugely important skill in Extension 2. And they have been doing these ramp type questions pretty commonly for the last few years. You typically see one every year or two. So definitely recommend you know how to handle a slope like this. So starting off, this mg, this weight vector that's going down here, we don't need this to go down. We need to have everything in the question working in two directions, either down the slope or off the slope. That's why they've given you an I and a j vector here. They're saying, hey, everything in this question needs to either go this way or this way. All right, so we need to break down this weight vector, mg, mass times acceleration, into this blue and red vector here, the blue one going down the plane and the red one going from the plane. Okay, so just going to need some more space. I'm going to draw this triangle over here with mg being the hypotenuse of this right angle triangle. Now we're going to need an angle inside this triangle, so I'm going to need to draw a bit more of a picture and include the rest of the sort of inclined plane here. So I'm just doing some dotted lines here to represent the plane with the angle theta just here. Now how are we going to get theta inside of our blue, red, black triangle here? Well, this is a right angle triangle, so think about it like if this was 60, then this one down here would be 30, which would make this one here 60 because we have a right angle here. No matter how you see it, you've got to figure out that these two angles match up. You can either think of them as like similar triangles, or I just think of it in terms of numbers. 60 here makes 30 here, makes 60 here. That's what works best for me. Okay, now we have this right angle triangle, and imagine that I drew a right angle here because I actually forgot. Getting an expression for the vector that's opposite theta and the vector that's adjacent to theta. The shortcut we can use is that the one across from this, or opposite theta, is always going to be hypotenuse sine theta. Okay, sine being opposite over hypotenuse, and if you rearrange it, you're going to get this, but I really just recommend you memorize that across from the angle is hypotenuse sine angle. And the one next to it, or adjacent to it, is always going to be hypotenuse cos theta. Okay, so that's the quick version of how you break down a vector like that. If you need more examples on that, I have a video in my Extension 2 playlist that's going to help you out with this mathematics here. Okay, now we're going to turn these two vectors and look at what's going on in the picture and turn them into some equations. So if we look at the vertical stuff that's happening, and by vertical I mean up with reaction force R and down from that. So we have our vertical forces. We have R going up in the same direction as J, so R is positive. And the red one that we said is mg cos theta, that's going down, so it's negative. Okay, we have R positive, we have mg cos theta being negative, and these two are resulting with a force of 0 because the object isn't going up or down. Okay, so there's no movement off or down through the ramp because that would make no sense. So these two forces are cancelling each other out, and that's how we're getting that 0 there. So that's not really going to help us. What is interesting is there is some motion going down the plane. So we really care about the blue vector here. And we're going to say that the horizontal force is just going down the plane. So because I is going up like this, we're saying up the ramp is positive. So down the ramp must be negative. So we have the force down the plane of the blue vector, which is mg sine theta. Okay, and there's a minus there because it's going down, like I said. Hopefully that's clear. Okay, so if we add these two together, we're going to get the total resultant forces on the object, which is going to be F vector. So adding those two together, we get the mg sine theta, which is the horizontal part. That's being multiplied by I because it's going in this direction. The vertical part, which we just said is 0, you don't really have to write this, but we have nothing happening in the vertical direction, so it's 0j. And this gets us pretty much straight to our answer, which is just the first part. So we have the resulting force is negative mg sine theta times I unit vector. Okay? Nothing happening vertically, everything happening horizontally to get our 2-mark equation right here. Okay, now that we have that, we can go on and answer part 2, which is using this equation to figure out the velocity in terms of g, theta, t, and I unit vector. So let's do that. Let's take that equation and we're going to turn it into velocity by using the fact that force is equal to mass times acceleration. So taking the answer from part I and changing force to be m times a. Now we can divide both sides by mass to get rid of these m's, and because we want it in terms of velocity and time, we're going to need to write acceleration as the derivative of velocity with respect to time. So cancelling off the m's, writing your acceleration as dv on dt. Now we can integrate both sides, and the left-hand side will get us velocity, and the right-hand side will be the integral of this. So keep in mind that g and sine theta are just numbers, so the right-hand side is really just a constant, and when you integrate a constant with respect to t, it just gets a t. Okay, so the constant gets a t and a constant because we just integrated. And now we'll figure out what that constant is by using our initial conditions. Initially, the object is at rest. So initially, when t is equal to 0, velocity is equal to 0. So we'll substitute that in, and we'll have 0 equal to negative g times 0 sine theta, which is just nothing. So we get 0 equals nothing plus c, which gets us that the constant is 0. So now we can go back to our equation and say, all right, cool, so our velocity is minus gt sine theta, but we need to turn this into a vector equation. So to do that, we're just going to multiply this expression by the direction that it's going in, which is in the I direction, because once again, it's only going down the plane, it's not going up or down. So we have velocity vector is equal to minus gt sine theta times I unit vector, and now we have velocity in terms of g, theta, t, and I as required. So really not a hectic amount of maths here. The challenge here was just being able to interpret the question and break down this vector into its components, and then just not get too spooked by all the vector notation getting in the way of the calculus. But there we go. As far as ramp questions go, this is one of the friendlier ones I've seen in recent years. Okay, moving on to something less friendly from 2022. This is a band 5 simple harmonic motion question. We have 2 positions of a single piston in the cylinder of a chamber of a motorcycle. So we're actually doing mechanics for once in mechanics. That's cool. Piston moves vertically, so it goes up and it goes down. The maximum height is 0.17 meters and the lowest height is 0.05 meters. That gets us our sort of oscillation, which creates a simple harmonic motion. The mass is 0.8 and the piston completes 40 cycles per second. So it goes up and down 40 times per second. What is the resultant force in the piston in newtons that produces the maximum acceleration of the piston? Give your answer correct to the nearest newton. Okay, so to access this question, we're going to need to find a force equation. And hopefully if you studied a bit of mechanics, you know that if you want to get a force equation, you need to get acceleration. So we're just going to write down our generic acceleration equation for simple harmonic motion. So it's acceleration equal to negative n squared x minus b. N is related to the period of motion and b is the center point of the motion. So if we can figure out a way to get this equation, we can then take our acceleration and multiply it by our mass to get our force, because force is mass times acceleration, because you've seen Star Wars. Okay, so center of motion, we can see if the max is 0.17 and the minimum is 0.15, the middle point that this piston is sort of oscillating around is going to have to be halfway between those two numbers. And halfway between 0.05 and 0.17 is 0.11. So straight away, just by figuring that out, we know what B is. Now to figure out what n is, we're going to need to think about the period of the motion. So the piston is doing 40 cycles per second, which means that it's doing one lap or one revolution in a 40th of a second. Okay, if something's happening 40 times per second, it means it's happening once every 1/40th of a second, if that sort of makes sense. So we're going to say, oh, also from this we can get that from 0.11 up to 0.17 and down to 0.05, so the distance of the oscillation is 0.6, and that's going to be the amplitude of our sine cos wave. Okay, so from the center point to the end points is 0.6. Okay, like I said, our period is equal to a 40th of a second because we're doing one lap every 1/40th of a second. Our expression to find the period of any sine or cosine wave or simple harmonic motion is always going to be 2 pi on n. Okay, you really need to know that the period of this function is 2 pi on n, because this equation is going to help us figure out n, and so we're closer to fully completing our equation over here. So we're going to multiply the n across up here and then multiply the 40 across here to get us that n is equal to 80 pi. Okay, so if the period is a 40th, it means the value of n in this equation is 80 pi. So now we can go over here and fill in what we know. We know that n is 80 pi, we've got a negative and a squared, and our center point of motion is 0.11. Okay, now we've got to think about the maximum force of this object. So part of the assumed knowledge for simple harmonic motion is that because the acceleration is directly proportional to the displacement, we know that the maximum acceleration of an object in simple harmonic motion is occurring at the endpoints when the displacement is the largest. Okay, so at the endpoint of 0.17 or the low point of 0.15, these are the points where like the curve is sort of turning around, and that's where you get your maximum acceleration. Okay, so max acceleration, max force occurs at the endpoints. Yeah, that's what I just said. All right, so you can pick either 0.17 or 0.05. I'm just going to go with 0.05 and sub that into our equation. Okay, when we calculate this, it gets us a value of exactly 384 pi squared meters per second squared. If you take the 0.71, you'll get the same thing, but it'll be negative, and then we're going to do a force, we're going to do magnitude anyway, so it doesn't really matter. You're going to get the same number. Okay? Okay, now we have our maximum acceleration. Now we can turn this into a maximum force by doing force equals acceleration times mass. So we just need to take this expression here and multiply it by 0.8 kilograms over on the right. Okay, force is mass times acceleration. So our max force will be our mass times our max acceleration that we figured out over here. Okay, and that's pretty much done. We get our 3 marks now for chucking that into the old calculator and getting a value of around 3,032 newtons, correct to the nearest newton. Okay, so for a question like this where there isn't a lot of guidance, just think about your equations, okay? Know your acceleration equations, know your period equations, and just think, what of the magic numbers, you know, the center point, the amplitude, the n, which of these can I figure out from the information in the question? Figure out those values, build your equation, and then you've got to rely on your knowledge of the motion to answer these high level questions. So yeah, pretty tough. Okay, on to question 3, which is from the 2021 HSC, and it was a band 4. This one's pretty tough. It's got a lot of working out, 2 3-mark questions, so 6% of the exam just here. We have 1 kilogram mass projected vertically upwards, initial velocity u, air resistance is kV squared, and k is a positive constant. That's going to be important. The height is x, time is t, and gravity is g. So everything's very straightforward so far. Show that the time for the object to reach its maximum height is given by this expression here. Okay, cool. So to do this, we're going to figure out our equation. So first of all, the force acting on our object, our 1 kilogram object, is going to be gravity working against us. So mass times acceleration. And we have the resistance mentioned in the question. It told us that it's kV squared. Okay, but because the resistance is also working against us, both of these expressions are negative. Gravity and air resistance both slowing us down. Okay, let's write our force as our mass times acceleration. Thankfully for this question, mass is just 1, so this mg just becomes g. And now we have our acceleration equation, and we can go forward and handle both these questions. Let's start off with part I. So when you get to this point, you've just got to figure out which of the 3 versions do I need to write my acceleration as. So what am I trying to achieve? I'm trying to achieve an equation that relates time to height. So time to No, I'm trying to find the time in terms of velocity because there's a u here. All right, so u is velocity. I'm trying to create an equation to link time and velocity. So I'm going to write my acceleration as dv on dt. Later on the question, part 2 is asking us to link two different variables, and we're going to start back from here and we're going to go with a different version of acceleration. But for this one, dv on dt is going to work. Okay, because the right hand side is in terms of v, we're going to need to take the reciprocal of both sides to make this look like this. And now if we integrate both sides, the left hand side is going to give us time and the right hand side is going to give us the antiderivative of this expression. Okay, so moving the dv across and then integrating both sides. While you're here, you may as well pull the negative out of the bottom of the fraction. Makes it a little bit nicer to look at. Now we've got to figure out how to integrate this, which is actually pretty tricky. So to integrate this, because we have a v squared on the bottom and there's no v's up top, we can't use any logarithms. So we need to use an inverse tan integration. For this one, which is pretty tricky because our standard inverse tan integration looks like this. We have a squared plus something squared on the bottom. On the top, we need the square root of a. Oh, sorry, we need a, which is, the square root of a squared, sorry. And we also need the derivative of the function that's being squared on the bottom to sort of apply the reverse chain rule here. So this is your standard integral for tan that you'll see on your reference sheet. We need to try and make this work for the equation in blue. So the trouble is that not everything on the bottom is squared, so it doesn't really look like what's in red here. So we need to do some clever manipulations here. The left-hand side, when we integrate it, is just going to turn into t, and we may as well just chuck our constant there for now. As you're going to see in this video, it doesn't really matter where you put your constants as long as you're careful. All right, so I'm actually going to write g as the square root of g squared, and I'm going to write kv squared as the square root of k times v squared. The reason I'm doing this is to make it look more like the standard integral in red in the line above, so I can say, okay, in this case, a is actually the square root of g, and the function that's being squared is root kv. So on the top of my fraction, I'm going to need a, which is actually the square root of g, and I'm going to need the derivative of the thing that's being squared, and the derivative of root kv is root k. So when I piece all that together, I can say, cool, so on the top, I need a root g and a root k to make it look like this, so I can apply an inverse tan integral. So because I just multiply the top by the square root of g and the square root of k, I need to divide by the square root of g and the square root of k at the front, so it keeps the balance, and now we're ready to proceed with our integration. So now this integral is going to be evaluated as inverse tan of root kv divided by root g. Okay, everything in red matching up with everything in blue down below. So t plus c is -1 over root gk, tan inverse of root kv divided by root g. Okay, that's probably the most hectic part of the question. Now we're just going to figure out what our constant is by using our initial conditions. So from the question, if we read back, initially it said that our initial velocity was u, so it's all very generic. So we're going to let t equal 0 and let v equal u, and we get this expression for our constant, okay? Constant equal to all this mess, not a single number in sight apart from a couple ones. Okay, we're going to put that into our equation, but remember, c is actually negative, and with my expression over here, c was on the left. So if I want to put that c across the right-hand side to make t the subject, it's going to change it from being negative to being positive. Okay, so my constant, just putting it over onto the right-hand side to make it positive, and you can see them matching up here, they're both green. So this is our expression for the time in terms of velocity for this, this particle. Now to answer the question, we're trying to find the time it takes for it to reach its maximum height. So if you've studied a bit of projectiles, you know that when a projectile reaches its maximum height, it's when it turns around and starts dropping. That's when its velocity is equal to 0. So we're just going to see what happens when v equals 0, which is when maximum height occurs for any projectile. All right, so starting into here, the front part is all just the same. It's still our constant. You can make it look a little bit more like the question if you want by taking the square root out of both k and g, but that's not really super essential. The important part is on the end where you do tan inverse of 0, and tan inverse of 0 is nothing. So the bit on the end just vanishes, and you get your time to reach maximum height, which is the target in the question, so we can put a QED and secure our 3 out of 3 marks. All right, so some pretty spicy calculus going on there. We're going to do some more now for part 2, where we're trying to achieve a different expression with the same starting point. So part 2 is to find an expression for the maximum height, but this time in terms of kg and u. So going back to our initial equation that we started from at the beginning of the question, Find expression for the maximum height in terms of k, which is a constant, g, which is a constant, and u, which is velocity. So reading this, I can think, all right, we're trying to find a link between height and velocity. Height and velocity is x and v. So that tells me for this question, or for this part, I need to write the acceleration as v times dv on dx. Okay, it's v and x because I'm trying to find an equation relating x and v. And that's how you got to interpret the question. Okay, so now this is our starting point, and we're trying to find an expression for the maximum height. So let's divide both sides by v. So just putting that under a fraction over on the right hand side. It's better to do it all as one fraction because now when you take the reciprocal of both sides like this, it's just a lot easier. We took the reciprocal because the right hand side is in terms of v, so now I can multiply the dv across and keep the dx on the left and do some integration. So integrating the left hand side, you just get x. I could have put a constant there if I wanted to, but I'm not done yet. On the right hand side, we're integrating this expression with respect to v, and again, I'm just pulling the negative out of the bottom of the fraction to make it look a little bit more friendly. Okay, now this time we have a v on the top of our fraction, so instead of using inverse tan, we can use a logarithm. So to use an integral with a logarithm here, we need to make the top of the fraction equal to the derivative of the denominator. So the denominator would differentiate to 0 plus 2kv. So I would really want the top of the fraction to be 2kv. So let's make that happen. Let's just put a 2k on the top and divide by 2k out the front to keep the balance. Now we can integrate using a bit of logarithms. So we have x equal to negative 1 over 2k, natural log of the absolute value of g plus kv squared with a constant. Okay, now we can go on and figure out what our constant is using our initial conditions once again. Question specified in the info dump that initially, when x is at the origin, so x is 0, the initial velocity once again is u. So we're going to substitute that into the expression. 0 on the left-hand side and u replacing v with our constant here. If we push this across the left-hand side, we're going to get that c is equal to positive 1 over 2k natural log of g plus k u squared. At this stage, because g and k and u squared are all positive, we don't really need the absolute values here, but we can just move on anyway. We can do that whenever we want. Okay, putting our constant back into our equation, which was up here. Okay, and because the constant is positive, when you've got two logarithms and one's positive and one's negative, it's best to put the positive one at the front to make your algebra a little bit easier, because now we're going to combine these two logarithms together. Okay, we have a 1 over 2k that's going to be at the front. And when you have log minus log, you can combine these together by using a division. So we're going to have x equal to 1 over 2k, natural log of g plus ku squared divided by g plus kv squared. Okay, this is just log a minus log b is equal to log of a over b. Like I said, because g, k, and u squared and v squared are always going to be positive, we should probably specify that. But at that stage, you don't need your absolute values because your expression can never be negative, so it doesn't really do anything. And there's our expression for x in terms of u and v. We're trying to find the maximum height to finish off. And remember, like I said before, maximum height of a projectile is when your velocity is equal to 0. So we're just going to set v equal to 0. And so we get 1 over 2k natural log of g plus ku squared divided by g. And that's our expression for the maximum height of the, what was it again? A particle or something? A particle. Anyway, there you go, 6 marks, 6% of the HSC done in like 10 minutes. Okay, on to the penultimate question now. This one is pretty tricky if you don't know how to set up the equations and understand what's going on with this pulley thing, but let's unpack it together. We've got a 2m and a 4m kilogram masses connected together on a light bit of string. So light meaning the string has no mass, which is, impossible, but anyway. We have a smooth pulley with no friction. Two masses are at rest before being released. V is the velocity of the larger mass at time t seconds when they are released. Okay, force due to air resistance on each mass has magnitude kV. So there's kV acting against both masses. K is a positive constant. Show that dV on dt is equal to g minus kV over 3m. Okay, to construct this equation together, we're going to need a better diagram, and we're going to have to sort of show what's happening here. So let's move this across up here. Okay, so first of all, let's talk about gravity. We have a gravity of mass times acceleration, so 4mg on the black mass moving down. This 2m mass also has gravity working down. But if you think about this, if there's 4m worth of gravity pulling this way on the black box, and there's 2m of gravity on the white box pulling this way, the way you got to think about this is this kind of results in 2m of mass going in the direction of the black box, okay? Because you've got 4m mass going down here. The 2m mass going down here is kind of pulling it away from V, and it's kind of going to make this lighter. That's how you got to kind of visualize this question, is the resistances on the white box and how they affect the resultant force on the black square. So we have 4mg going this way, 2mg going this way, but it's actually going up, okay? So think of this 2mg as going up because it's going around the bend and pulling the black box up, is how you got to try and think about it. Anyway, this one's confusing. Sorry if I'm not explaining it too well. We have our resistance on both of them being kV, and resistance always works against your motion. So because the black box is going down, the kV is working against us and working up. Similarly for the white box, because we have the white box moving up the pulley, the air resistance is moving against it, which is moving down. Okay, so we have 2 bits of gravity, but one of them is actually working for us, one is working against us. The air resistance are both working against us. Okay, so now let's create our equation. So taking the motion of the block, so they're moving this way around the bend, we have force, we have our gravity working with us because we're moving down, and we have resistance, air resistance always working against us. So we have our 4mg going down, we have our 2mg, which is really going up because it's going around the bend. That's why I'm doing 4mg minus 2mg to get a resultant force of 2mg going down. Our resistances, both air resistances of kV working against us, so these are going to go together to make minus 2 kV. Okay, so from this we get 2mg on the right and we get minus 2 kV on the right. Now the tricky thing is the mass on the left hand side. Now think about these 2 blocks are connected by a bit of string, so you have to kind of think of them as one object, okay? Because they are connected, they have one entire total mass of 2m plus 4m, which is 6m. I think that's the part that a lot of people struggled with in 2020 to sort of piece this together. Even though the 2m gravity is working against us, the entire object is connected and the entire object has 6m mass. Okay, once you got that set up, from here it's pretty easy because now we're just going to divide both sides by 6m to get this fraction. And now we have a lot of even numbers everywhere, so we can just cut everything in half to get mg here, to get kv here, and to get 3m on the bottom. And that is your QED for 2 marks. Okay, that's the tough part, is getting this equation and making it make sense from the picture. Okay, now we have that, we can have a stab at part 2, which is, given that velocity is less than gm divided by k, show that when time is equal to 3m over k log 2, the velocity of the larger mass is gm over 2k. Okay, so we have our equation over here, dv on dt. We're just going to take the reciprocal of this because the right hand side, the only variable we can work with is v, and v is on the top. So first thing we'll do is flip the equation to get dt on dv equals the inverse of the fraction. The reason we did that is because now we can move the dv across and integrate both sides, as we've done a few times this video already. So the left hand side is going to get integrated with a 1 dt. The right hand side is going to get integrated with the dv, and because 3m is just a constant, we can just pull that out the front to make our lives a little bit easier. Okay, so left hand side is just going to integrate to t with a constant, or you can put your constant on your right, you can do whatever you want, I'm not going to stop you. To integrate this fraction, we need to make the top the derivative of the bottom so that we can use a logarithm once again. So derivative of the bottom, the mg is just a constant, so that just differentiates to 0. Minus kv differentiates to minus k, so I'm just going to put a minus k on the top and a minus k dividing out the front. Now that I've done that, I can integrate the right hand side using a logarithm. So I get t plus c equals negative 3m over k, natural log of mg minus kv. Now, the information in the question relating v to gm on k, this is actually information that you can use to figure out why you don't actually need these absolute values here. Because if v is less than gm over k from the question, if we times that k across, we get that vk is less than gm. And then if we move that vk across to the right, we get that 0 is less than mg minus kv. This is basically our argument for saying that the inside of our logarithm is always going to be positive from the info in the question. So because it's positive, we don't need to have our absolute values here, and we can just say it's just a log of the inside. It's always positive, okay? So writing that like that, we're now going to figure out what our constant is with our initial conditions. So initially it said the objects were at rest. So when t equals 0, v equals 0. Subbing that in, we get 0 plus c is equal to negative 3m over k times natural log of mg minus nothing. So we get our constant as negative 3mk over log mg. Because that was on the left, if I want to put it over to the right in my equation, it's going to become positive. So I'm just putting that on the right as positive to get t by itself, as I've done already today. Reason I'm putting it on the right is because I want to merge these two logarithms together. So like I said, it's best to have the positive logarithm first and then the negative one second. Because now we can just factor 3m over k out the front, and once again do log a minus log b is equal to log a over b. So here is our expression for the time of the blocks in terms of logarithms and velocity. To answer the question, it said that show that when time is equal to this, the velocity is equal to this. So we're going to set the left-hand side for time equal to 3m over k times log 2. Okay, taking the equation and making the left-hand side the time given to us in the question. This actually works out really nicely because on both sides we have a 3m over k logarithm, So for the left-hand side and right-hand side to be equal, we just need mg over mg minus kv to be equal to 2. So everything else just cancels out. Now we're just trying to find velocity. So to get our final mark, we just need to rearrange this equation to make v the subject. So I'm going to multiply the denominator over across the left-hand side. While I'm doing that, I'll divide the 2 across the right-hand side to make mg over 2. Now I can subtract mg from both sides, and on the right I've got a half of mg, take away 1 mg. So a half take away 1 is equal to negative a half. So that simplifies quite nicely. Now I can take the negatives off both sides and divide by k, and I get v equals mg over 2k, which was designed to be the target from the question. So we just got 3 marks in a pretty challenging band 5 HSC mechanics question. Okay, this is hard work. I think we're up to the final question now, which is a bit of resisted projectiles. It is. So resisted projectiles are mentioned specifically in the syllabus, but they weren't really assessed up until 2023. So it's hard to say whether these are going to be a regular part of HSC because they weren't tested for 3 years. But then last year, my prayers were answered and NASA gave us 7 marks worth of resisted projectiles. So I'll take you through every single part. The first part is only band 3, but the parts at the end are more band 4, 5 level, much more challenging. Okay, we have, what time is it? Have I been doing this for like 10 hours? Yeah, more or less. Okay, we have mass 1 kilogram, we have speed 40 meters per second, and we have an angle of projection of 30 degrees. Using that information, show that the initial velocity vector of the particle is 20 root 3 horizontally and 20 vertically. All right, that's a nice, easy starting off point. So starting off with our initial conditions for a projectile, as always, initial x velocity is equal to u cos theta. So u is 40, being our initial velocity, and theta is 30. So we get initial x velocity as 40 cos 30. Cos 30 is root 3 over 2, so we just get 20 root 3, which is the required x component. For our vertical velocity, the initial component of a projectile is always going to be u sine theta. So we're doing 40 times sine 30. Sine 30 is just equal to a half, so we get 20. So we can very quickly establish that 20 root 3 and 20 are our initial components. So 1 mark, nice and easy. Moving on to the real pain now, which is part 2. We have forces acting on the particle, we have gravity, and we have air resistance. Air resistance is proportional to the velocity with a constant proportionality 4. Let the acceleration be 10. So we have our velocity vector given by this, and we need to show that this is our velocity vector for 3 marks. We need to get the x velocity, and we need to get the y velocity with a lot of integrating and a lot of constants and a lot of messing around. So let's set up our equations. We have our initial from part A, that's going to be very useful. Now for our vertical acceleration, so we have mass times acceleration to make our vertical force. We have air resistance proportional to our velocity. So we have air resistance here, k times y velocity, and it's negative because air resistance is always working against us. For our vertical, because we're being fired from the ground, we have gravity working against us. So we have force equals mass times acceleration for gravity, negative because it is working against us. For our horizontal component, we have the same thing but without the gravity. We just have the air resistance working against us in the horizontal capacity. So horizontal force is equal to, we have our resistance, which is proportional to our x velocity. So the notation for these questions can get a bit hectic, so try and stick with it if you can. So turning these green equations into actual equations we can use with the information in the question. We have our mass is equal to 1, which is nice. We have our air resistance proportionality constant, the thing out the front, the K, is equal to 4. So we have -4 here. And they're just letting gravity be equal to 10. So on the end, our mg is 1 times 10. So there is our vertical acceleration equation. For the horizontal one, like I said, it's the same thing without the gravity. So it's -4 times velocity. Okay, cool. So we're going to try and turn these two acceleration equations into two velocity equations and make them look like this to get 3 marks. So let's have a crack. Let's start off with the vertical, starting off with our acceleration being equal to the derivative of our velocity with respect to time. So this is like dv on dt, but we can't use v because it's too generic. We need to have y dot and x dot so we can communicate to our marker which dimension we're working in. The right-hand side is in terms of velocity, so as always, we're going to need to take the reciprocal, and while we're doing that, we may as well just yoink the negative out the front and make it look a little bit more friendly. Now we can integrate both sides. So the left-hand side, when we integrate this, we're just going to get t with a constant. On the right, we want this to have the top of the fraction being the derivative of the bottom, being 4. So I'm just going to put a 4 on the top and divide by 4 out the front. Now I can integrate this using a logarithm to get natural log of 4y velocity plus 10. Okay, for these questions, little tip, before you find your constant, it is going to make your algebra a little bit more friendly if you just multiply everything by -4 and just get a logarithm here, okay? It'll still work if you don't do that, but just I'm telling you, it just makes it easier. Luckily, when you multiply a constant by -4, it's still a constant, so you can just leave that as c and it's all good. Okay, so initial conditions, our initial velocity for y is equal to 20. So we're setting t equal to 0 on the left-hand side, and we're setting y velocity to be equal to 0 from the information in part I. This gets us that nothing plus c is equal to log of 90. Okay, so our constant here on the left is log 90. So we're just going to put that over to the right and make it negative. Okay, again, you could have just put your constant on the right. It doesn't matter, as long as you keep track of everything, it's all good. Okay, so constant on the right being negative log 90. Now we're going to divide everything. No, sorry, we're going to combine these two logarithms together because we're trying to make the y velocity the subject and make it look like this. So combining our two logarithms by using a division once again, we can now get rid of our logarithm by raising both sides to the power of e. So the left-hand side becomes e to the negative 4t, and the right-hand side, we don't have a logarithm anymore. Now, because the other side is e to the power of something, e to the power of something is always going to be positive, so you don't need your absolute values anymore, and you don't need a plus minus, okay? E to the minus 4t, always positive, always good. Now we're just going to rearrange to make y dot the subject. So we're going to multiply the 90 across, and then we'll subtract the 10 across. And then if we just divide everything by 4, we get 90 divided by 4 is 45 on 2, and 10 divided by 4 is 5 on 2, and that red equation there is half the target prescribed in the question. So we're halfway there. Oh god, I think my voice is going. Okay, now let's do the same thing with the horizontal velocity. So starting off with our horizontal acceleration, which is -4 velocity. Once again, we're going to take the reciprocal of both sides to put the velocity on the bottom. And now we can integrate both sides to get t on the left and to get the integral of this on the right. Easiest way to integrate this is to pull the quarter out the front, and so you're just doing the integral of 1 over x dot. And so once again, we can just use a logarithm here, and we can have t plus c is equal to -1/4 ln of x dot. Okay, integration done. Next step is to find our constants. Like I said, it's a little bit easier on the algebra if you multiply everything by -4 first. To make it look like that. Now we can say that our initial x velocity from before in red is 20√3. So with the blue equation over here, when t is equal to 0, x dot is equal to 20√3. That gets us that c is equal to 20 log of 20√3, but that's positive on the left-hand side. We're going to put it over on the right to be with the other logarithm, so it's going to become negative. Okay, log 20√3 on the left is negative log 20√3 over on the right, which probably tells me I should have just done my constant on the right, but it's too late now. I've already done the lesson, so we're just going to move on. Okay, we're going to combine these two logarithms together by doing a division, log a minus log b type stuff. We're going to raise both sides to the power of e. Once again, now we have e to the power of something. This only gives positive answers, so the absolute values are not required. And now we just multiply the 20 root 3 across, and we get 20 root 3 e to the minus 4t, which was the target for the x velocity. So both parts are done for 3 marks, and I'm already exhausted, and we're about halfway through. Okay, let's move on to the next part, which is to find the x and y position vector. So x and y position vector looks like this, and we're going to try and obtain these two equations for 1 mark each, giving us 2 marks in total, and then to finish off with part 4, which looks scary, but it's actually very, very friendly. Okay, so for part 3, we're going to take our two velocity equations, and we're going to turn them into displacement equations. So because this is in terms of t, starting off with our vertical component, which we established before, because it's in terms of t, to get from velocity to displacement, all you've got to do is integrate with respect to t. So integrating both sides. On the left, when we integrate the derivative of y, we get y. When you integrate an exponential function, it stays the same, but all you've got to do is divide by the derivative of the power, which in this case is minus 4 is the derivative of the power. The minus 5 over 2 gets a t, and the whole thing gets a constant. We can tidy this up slightly because the 2 on this fraction is going to sink down below and make that a negative 8, but you don't have to do that. Let's figure out what our constant is by using our initial conditions, which is that when when t is equal to 0, we are at the origin, so y is equal to 0. So the 5 on 2 is going to vanish away. E to the power of nothing is equal to 1, so we're going to get just negative 45 over 8 plus c is equal to 0. When we solve that by putting the negative 45 over 8 across the left, we're just going to get that the constant is equal to 45 over 8. So putting that back into our equation up here, it looks like this. And we're trying to make it look like this, and we're pretty close. All we've got to do is factor the 45 out of 8 out of these two things. So 45 over 8 out the front, 1 minus e to the minus 4t with the minus 5 over 2t on the end. And that is our y component done. So there's our first mark. Now we're just going to do the same thing with the x component. So starting off with our x velocity equation that we established in part 2. Integrating both sides with respect to t. When you integrate velocity, you get displacement. Once again, integrating this, we're going to keep it the same. All you need to do is divide by the derivative of the power, which is minus 4 once again. Initial conditions, initially when t is equal to 0, we are at the origin, so x is equal to 0. 20 over 4 is equal to negative 5, that's pretty clever. X equal to 0 when t is equal to 0, so we get 0 equals minus 5 root 3 times 1 plus c. Solving this gets us that our constant is 5 root 3. Now we just put that back into our equation. We're going to put it at the front because it's positive. Okay, so c being 5 root 3 going to the front. Now we just factor the 5 root 3 out of both expressions, and we get the required target of 5 root 3, 1 minus e to the minus 4t for your x position. Okay, so that wasn't too bad. Just a bit of integrating and a bit of constants. Fun stuff. Moving on to the final part, which is, hey, here are the graphs of y equals 1 minus e to the minus 4x, and here's the graph of y equals 4x over 9. We can see the diagram, and we can see that these guys cross over at approximately 2.25. Using this diagram, find the horizontal range of the particle, giving your answer rounded to 2 decimal place, or 1 decimal place. Okay, so let's think. How do we find the horizontal range of a particle? Well, the way we find that is we find when the particle lands, which is when the height, or the y value, is equal to 0. So particle lands when y displacement, vertical displacement, is equal to 0. So taking our equation that we established in part 3 for the y component, and we're going to set this equal to 0. All right, so let's see what happens. Let's move the 5 over 2t across. Let's multiply both sides by 8. And now let's divide both sides by 45. And what you end up with is 1 minus e to the 4t equals 4t over 9. Hey, that's really similar to what it looks like in the question. We already have the graph of 1 minus e to the minus 4x, and we have the graph of 4x over 9. This picture tells me that these two cross over at approximately 2.25. That tells me that this equation has solution at approximately t equals 2.25. That's when the left-hand side and the right-hand side are equal. So we say, cool, this is approximately solved by 2.25. So we know the time when it lands. If we want to find the horizontal range, we just want to find the x value of the particle when it lands to find the horizontal range. So we take our x equation established in part 3, we're going to let t equal to 2.25, and that's going to get us our approximate maximum horizontal distance of about 8.7. Okay, so there you go. There is, I think that was like 3, 6, something. That was 8% of the 2023 HSC on a topic that they'd never assessed before. So luckily, as long as you're familiar with projectiles, it's all pretty similar stuff, just with the extra challenge of the calculus being more challenging with the resistance. But other than that, it's all stuff that you know how to do. It's all integration. It's all rearrangement. It's good fun. Anyway, hopefully these examples have given you a bit more confidence with mechanics, and it's going to help you prepare for your HSC. So good luck for your study over the next few weeks, and I hope that the extension to exam is nice and friendly and allows you to demonstrate a lot of what you've learned in the last year, and hopefully I've been some form of help in getting you ready for that exam. Okay, I'll still be putting out a bit of Extension 1 content before the HSC if I get time, so keep an eye out for that. And yeah, thanks for watching, and I hope you're learning, and I'll see you next time.